Thank you, Roland, and thank you everyone for attending this morning. It's a great pleasure of mine to talk about this work. And before I get started, let me also thank the organizers, Roland, David, and of course Birgit, who's not here, but maybe perhaps she'll be watching this at some point. And so thank you to future Birgit. And so today I'd like to tell you a bit about exactly what Roland said. So particularly stable blowup for the higher dimensional Skyrme model. And so a bit of history first. So this model, the Skyrme model, came out of nuclear physics in the 1960s as a way to correct the expected formation of singularities present in the so-called nonlinear sigma model. And so the nonlinear sigma model was, at this time, a way that physicists, very roughly speaking, tried to model nucleons inside of atoms. And so, but it had one fatal flaw in it, namely scale invariance, which they believed at that time led to the formation of a singularity. And so let me go ahead and provide some context here first. So the way in which I will present the Skyrme model is, of course, a generalized version of it. It's not exactly how the physicist Tony Skyrme presented it at the very beginning. Nevertheless, there are 4 bits of, depending on how you count, 4 or 5, I forgot how to count, 4 bits of important information. Namely, I'm going to have 2 non-negative parameters, alpha and beta, which I will play with throughout the talk. So alpha and beta will on occasions be both 1 or both, or only one be 0 or both be 1. And there's also beta, which I'm going to refer to as the Minkowski metric. But it will very quickly vanish, and so I'm not going to bother giving a sign convention or anything like this. There's also H, the round metric, on a D sphere, and then maps U from R1 plus D into the D sphere. So the Skyrme model is a geometric field theory, namely it is a field theory derived from a Lagrangian. And so this Lagrangian is, in terms of maps of this form, so this Lagrangian I'll call L, and it begins with the Lagrangian of the nonlinear sigma model, or namely wave maps into a sphere, given by, so there's this parameter alpha, which I'll throw in front of the wave maps term, divided by 2 for convention. And then we pull back the round metric from the sphere onto Minkowski space along the map U, and then contract this with the Minkowski metric. Here, of course, I'm using the Einstein summation convention, as well as working in a system of coordinates where all of these derivatives make sense. And so as I go forward, I want you to think of these terms as, of course, this is the Lagrangian of the wave maps, of wave maps into a sphere. And so I will be repeatedly calling these the wave map terms. And everything that appears next to this parameter alpha, I will be calling, broadly speaking, wave maps terms. And so, but of course, this is not all there is to the Skyrme model. There's another term, the correction term, which Skyrme introduced, which I will throw down here, which comes paired next to some beta divided by 4, which is precisely which precisely plays the role of breaking scale invariance, thereby, at least in 3 dimensions, preventing the formation of a singularity. And sorry, is there a serious echo when I get near the board? I can hear it. No? Okay, good. So it begins by starting off with the wave maps Lagrangian, which, in fact, because it's a bit of a hard thing to look at, and I want you to think of this as, this is, of course, the trace of the linear transformation I get when I pull this metric back to the Minkowski space. So this I want you to think of as the sum of eigenvalues of that linear transformation. And so I'm labeling coordinates on Minkowski space x0 through xt. And this next term is in fact going to be the sum of pair products of these eigenvalues. Okay. So in other words, this next term, which I'm about to write, is lambda 0 times lambda 1 plus all ways in which I can pair distinct eigenvalues and sum them up. Okay, so I get lambda d, lambda 1. Okay. And so the way in which we get this is by first squaring this quantity. So it's eta mu nu, HAB, d mu UA, d mu UB, this squared. But of course, if I square this, then I get lambda 0 squared, lambda 1 squared, and so on and so forth. So I subtract the diagonal terms, and this ends up being HAB u mu UA, d mu UB. And then another copy of this, which I'll use indices Hij of u, the, let's call it rho, ui, the sigma uj, and then contracted again with the Minkowski metric. But this chunk gets paired with this chunk through a and I, or I'm sorry, mu and rho. Mu and rho, eta nu sigma. Okay. And so this term cancels precisely those diagonal terms in squaring this. So this is the Lagrangian density of the Skyrme model. And what's most important is that these terms, as we can see, the purely Skyrme terms, which I'm in fact going to give a different name in a moment, are fourth order in the derivatives as opposed to the wave maps terms, which are quadratic in the derivatives. And precisely this is responsible for breaking the scale invariance present in the nonlinear sigma model. And so going forward, I'm going to call these the strong field terms for reasons that will be justified shortly. So, as a consequence of this difference in order of derivatives and how they appear in the Lagrangian, so in fact, make this clear, the entirety of this is the strong field term. And so due to the difference in order of the appearance of the derivatives, the corresponding Euler-Lagrange equation ends up being a quasi-linear system of PDEs for the field U. But I don't want to look at this equation in its broadest generality. I'm instead going to look at a subclass of such maps called co-rotational maps. And so I'm going to look at these maps, which play nicely with the geometry of the domain and codomain. And I'm going to specify them in the following way, namely that if I were to put spherical coordinates on Minkowski space, which I'll denote by T, R, and omega, where here omega is d minus 1 angles on the codomain, then a co-rotational map is going to select a polar angle on the target and allow all of the other remaining angles to vary. And that one polar angle which I've selected is going to allow, I'm going to allow it to vary with time and space in a radial way. And for such maps, the equation of motion for capital U reduces to a single quasi-linear wave equation for the variable, for the new unknown C. And so this equation, of course, is going to be the main object of this talk, so let me tell you what that works out to be. So with these parameters alpha and beta, it works out to be alpha plus beta times d minus 1 sine squared c over r squared times ctt minus crr plus alpha plus beta d minus 3 sine squared c over r squared d minus 1 over r, CR. And then plus some more nonlinear terms. d minus 1 and 2c over r 2r squared times alpha plus beta, and then ct squared minus cr squared plus d minus 2 sine 2c, sine squared c over r squared. Okay. And so this is the main equation of study, which I'm going to call equation star, since I'm going to refer to it many times. And so in particular, there are a couple important things to observe here, namely that this is, as I mentioned, a quasi-linear wave equation because, well, the highest derivative terms, of course, are nonlinear in C. And moreover, as a consequence of the breaking of scaling of the Lagrangian, this is still very naturally a non-scale invariant equation. And this can be seen pretty straightforwardly if we just look at the first term. If I were to look at CTT times alpha, this scales like 1 over space-time squared. Whereas if I were to look at beta times CTT, this scales like 1 over space-time to the 4th. And so we can see immediately the breaking of scale invariance here. And so, and since it's a wave equation, the main problem of interest that we have is, of course, the Cauchy problem. If I specify some initial conditions, do I get solutions that exist for some amount of time, or maybe perhaps some infinite amount of time? And the usual heuristic is we first look at the conserved energy and observe how the energy rescales under scaling of the coordinates. And so there's, of course, the conserved energy that this equation admits, whose particular form is not going to be important for us, except that it decomposes in the following way. There's a portion, so of course it's obtained in the usual way by multiplying by CT and integrating by parts. And so there's going to be a portion coming from alpha and a portion coming from beta. And so this works out to be something of the form alpha times what I'm going to call E2 of C plus what comes from the beta portion, the strong field portion of the equation, beta times E4 of C. And so this is the form of the conserved energy. So in fact, E2 of C is precisely the conserved energy of a wave map from RD plus 1 into SD. And then the E4 portion is, if I were to just have looked at the conserved energy corresponding to this portion of the Lagrangian for a co-rotational map, that's precisely this. And so, using the usual heuristic, we might consider looking at how this equation and its conserved energy behave under rescaling. And of course, you should immediately be skeptical that, well, as I mentioned, this is not scale invariant, so what does it, upon rescaling this solution, I don't get another solution, but nevertheless, I'm going to be arrogant and do it anyway. And so, if I were to rescale, namely, if I were to take a solution, or just a function that I want to measure with respect to this conserved energy, and I were to define something new, C lambda of T and R, defined to be, I just take this original thing, C, and I rescale the coordinates in this way. So here lambda is some positive scale. Then what I'm going to find is I can relate the energy of C lambda to that of E in the following way. The energy of C lambda at time t, but I'm not going to bother writing this, is precisely alpha times lambda to the d minus 2 times the E2 portion, the wave maps portion of the energy of C, plus beta to the lambda, beta times lambda to the d minus 4, E4 of C. And so very obviously, there's there are different exponents appearing on this factor lambda. And so this might suggest that it's at least worth looking at the various cases that we can find ourselves in. So for instance, here's one case that's worth looking at, E equals 2, namely where we have the energy critical scaling of the E2 portion of the energy, but energy subcritical scaling of the strong field portion of the energy. And so I'm going to divide further into subcases, namely when alpha, or rather when beta is 0 and so on. And so when beta equals 0, this is something that has been studied over the last several decades, which we know a lot about, and I'm not going to attempt, of course, to summarize this literature. But when beta equals 0, this is exactly the critical wave maps equation from R1 plus 2 into S2. And we know a lot about the formation of singularities for namely finite time blowup. Namely that we have singularities due to the existence of solutions of the form which rescale the ground state harmonic map from R2 to S2. So we have this ground state harmonic map, Q, which can be rescaled by some dynamical rate lambda of t. And this is in fact a true solution up to some error, which is small compared to the rescaled harmonic map, where this lambda of t goes to 0 as t approaches some capital T called the blowup time. So capital T being here some positive number. And so we know this. This is, there are many works in this direction. So just to name some, we have the groundbreaking works by Krieger, Schlag, and Tataru. From 2008, as well as the works by Rodniansky, Serbins in 2010, and Rodniansky, Raphael in 2012, which for various blow-up rates show that you have solutions of this form. Nevertheless, as soon as you set beta not equal to 0, for instance, just for simplicity's sake, let's say alpha and beta are both 1, then you no longer see this. So this is due to a work of Matthew Creek. So if beta is not equal to 0, all of a sudden you have global existence for large data measured in the proper Sobolev space. And so this is in fact due to Creek. You have, let me say, global existence. Or in other words, you do not have the formation of a singularity. As I mentioned, this is due to Creek, Matthew Creek, from 2013. In fact, if you look at this paper, it's for the equivariant Fadeev model, but however, it's precisely equation star. It's precisely this when you set d equals 2. And so this was then optimized by Jabba and Grelakis a few years later in 2017. And so initially, this at least demonstrates that as soon as you add this strong field term in low enough dimensions in dimension 2, where you have this subcritical scaling of the strong field portion, you prevent the formation of singularities. And furthermore, in dimension 3, this persists. So in dimension 3, we still see the same thing, namely that now we have, for the wave maps portion of the energy, we have the supercritical scaling, namely that as lambda goes to 0, this portion of the energy also goes to 0. But we still have the subcritical scaling of the strong field portion of the energy. So again, if beta equals 0, we know quite a bit about this. Again, singularities can form, but now through the existence of exact self-similar solutions. So we have solutions, CTR, which are precisely 2 times the arctangent of, all right, like this, R divided by capital T minus little t. Where again, here capital T is what I'm going to call the blow-up time, where, for instance, if I were to set t equals to 0 and correspondingly for its time derivative, then I can evolve this initial data and get something which develops a gradient blow-up at time capital T. So there are lots of works in this direction, which namely in particular, it's the stability of this solution, which again, I'm not going to attempt to accurately summarize, so let me name a few earlier works. In particular, the stability of this solution has been intensively studied over the last decade and a half or so. There's works by Roland Donninger, dating back to 2011, as well as Eichelberg, Donninger, and Schorkhuber. In 2012. And then these two results, I should say, were that assumed what's called the mode stability of this solution, and then mode stability was then resolved by Irfan Gogic in 2018. And so, but again, the same story is true. As soon as beta is not equal to 0, now you no longer have the formation of singularities. In particular, as soon as beta is no longer 0, again, as I've pointed out many times now, you again have the subcritical scaling for the strong field portion of the energy, while you simultaneously have the supercritical scaling of the wave maps portion of the energy. And in fact, again, you have global existence for large data. And so this result is due first to Dong Li from this, while this was published in 2021, this first appeared on the archive in 2012. And so the technique he developed was to realize you can take equation star and transform it into one without a derivative nonlinearity. In fact, this corresponds to integrating that factor appearing in front of, roughly speaking, in front of CTT minus CRR. And so then he was able to develop some bootstrap argument to obtain global solutions from local ones. And then this, again, these techniques were optimized by Jabal and Grilakis in 2018. And so, at least in low dimensions, low meaning 3 or 2, it appears that the addition of the strong field term precisely prevents the formation of singularities. However, clearly, if you look again at the energy rescaling relationship, something different happens in d equals 4, namely that this exponent changes. In fact, I won't even bother writing the d equals 4 case because this is completely unexplored. And so all I'm going to say is that nothing is known. So I'm going to skip immediately to dimension 5, where this result I want to discuss lives. So in dimension 5, we again have the supercritical scaling for the wave maps portion of the energy, but this time the qualitative behavior has changed. We now have the supercritical scaling for the strong field portion of the energy. And so we have a similar story. If I were to set beta equal to 0, we have, again, this solution is known in all dimensions, so we have blow up according to this, at least when beta is equal to 0. But now something new happens, which is precisely in alpha equals, in the case that alpha equals 0. And so again, in this case, in fact, singularities can form via the existence of self-similar solutions. And so I'll say there are self-similar solutions. And so this was first proven by myself in 2020. Well, it appeared in 2020. But the argument I gave was very much along the lines of Chattah's original proof of the existence of the abstract existence of this solution. But then I can give you a one-line proof due to Birgit-Schortgruber. So I'll say this is due to Schortgruber. That, in fact, there is an explicit solution, which is precisely 2 times the arctangent of 2 times rho divided by the square root of 5 minus rho squared, where rho is precisely the self-similar variable r divided by capital T minus little t. And so there exists an explicit self-similar solution of the alpha equals 0 limit of this model. And so together with Chen, Poning Chen, my PhD advisors, Chen, Schortgruber, we in fact, came out last year, we proved that this family of solutions, I'm going to give this a superscript CT because I want to refer to it later. This family of solutions is stable. And so I'll give a statement of this that looks a bit more precise shortly. However, this family of solutions is stable. And so starting from this, precisely this family of solutions, turns out, as the result I'm about to share with you shows, that you can obtain stable blowup starting from this solution for the alpha and beta not equal to 0 model. So this brings me to the main result of the talk. Which I'm not going to give a date for it because it hasn't appeared yet, but it should very soon. Which is that, roughly speaking, starting from a small ball around the initial data I obtained from this solution, I can evolve that according to this equation and get a solution which remains close to some time-translated version of this, plus some error, which is small, close to the blowup time. So just to restate that more precisely, so if I set alpha and beta equal to 1 and d equal to 5, then there exist positive constants. Yeah, I'll state it like this. There exist positive constants such that the following holds. Namely, for any lambda, which is sufficiently small, this is in fact going to parameterize how small the blowup time is that I begin with. And so for any small parameter lambda and smooth perturbation, so C0, C1, which are both radial functions, and there's C2 and C1, defined on a ball of radius 2 delta, defined in 7 dimensions. The 7 dimensions is, of course, 2 higher than 5 dimensions, and this is coming precisely from that we're working with a co-rotational map, and I'll clarify that in a moment. So starting with any such initial perturbation, which are small in the following sense, that the following norm of this solution. So if I divide by some radial factor and measure these in the Sobolev space, H7 cross H6, the ball of radius 2 delta in 7 dimensions. If this is small in the precise sense that there's this smallness parameter depending on the scale, lambda, which appears to the 5/2, times delta over C, then there exists a unique, in fact, there exists two unique things. There exists a unique T between 1 minus delta and 1 plus delta, and classical solution, C, of equation star, such that initially I am a small perturbation of the solution which blows up at time lambda, the self-similar solution of the beta of the alpha equals 0 model. Namely, initially my solution looks like equals the solution which blows up at time lambda. So lambda is small, so this initial data, if I were to evolve it according to the strong field limit of the model, this would blow up at time lambda at a very quick blow up time. If I were to perturb this by C0, and then similarly, of course, for the first T derivative, you get then the solution remains close to the solution which blows up at time lambda times T. Equals the solution plus some remainder, which I guess I'll call epsilon. And epsilon goes to 0 in some precise sense at rate omega. Okay. But I won't specify that precisely. Epsilon goes to 0 in a suitable sense. As T approaches lambda times capital T from the left. Okay. So to restate that one more time, starting from a small perturbation of the self-similar initial data, which would have, in the alpha equals 0 subcase, would have blown up at time lambda, I in fact, in the case where alpha and beta are both non-zero, when alpha and beta are both 1, I in fact get a solution which remains close to a time rescaled variant of this, precisely this. Oh, I should have called this capital U. My apologies, I started writing capital U and never told you what it was, so hopefully you read my mind without me saying it. So capital U is precisely the blow-up profile, appearing the 2 times arctangent thing. And the solution remains close to a time rescaled version of that solution. Okay. All right, very good. So let me make a quick few remarks. So I have 50 minutes, right? So, okay, cool. So let me make a few remarks before I tell you a bit about the proof of this. So of course, there's the question of topology. How do I measure the smallness of this norm? And in fact, this convergence to 0 is taking place in, I should have said, H6 cross H5. And so this is precisely, so H7 ensures 4 things for us, namely that, 1, we have L infinity control of our solution. And this is to deal with the fact that at some point we divide by sine of C. We want to make sure we stay away from the zeros of this. Moreover, we want L infinity control of the derivatives so that we can estimate those in our fixed point arguments, which raises it, which gives us some level of regularity we need to work with. And then furthermore, we want to have a classical solution, so we want at least a C2 solution. So this requires, again, another one more bit of regularity. And then to get something which I should have said, we actually have Lipschitz dependence of this solution on the perturbation and on lambda on the scale. And this requires one more derivative in smallness than where the convergence takes place, as I said, which takes place in H6 cross H5. So that's where this regularity assumption is coming from. Okay, so for the remainder, the remaining like 12 or so minutes, I'd like to tell you a bit about how this proof proceeds and how it in fact reduces to the alpha equals 0 model, what I did with Poning Chen and Birgit Schwarz-Huber. So let me tell you a bit about the proof. So the idea is to make some precise sense in which I can treat the wave maps terms appearing in the equation as negligible compared to the strong field terms. This seems at least mildly reasonable looking at the energy rescaling relationship in D equals 5, where this is lambda to the 3, and correct my arithmetic if I mess it up, and lambda to the 1, where at very small scales, lambda to the 3 is small compared to lambda to the first. And so this is in fact precisely why this blow-up time, this initial blow-up time has to be very small. So initially, I can make sense of the wave maps terms as small compared to the strong field terms. However, they could grow in size. They could have a non-trivial influence to the evolution. However, precisely due to the lack of scale invariance, I in fact maintain this smallness, which is most easily seen by transforming to similarity coordinates. So let me tell you a bit about this. So first, I want to transform to similarity coordinates. But in fact, before I do that, I also want to remember that I'm working with a co-rotational map, which also comes with the added condition that to ensure finite regularity at the origin, I need to impose a boundary condition, namely that at 0, at r equals 0, the solution is always 0. So if I were to look at the function with this vanishing factored out, namely u of tr, then I can very easily see this, this maintaining of smallness factored out. So in other words, I'm going to switch to the coordinates tau and rho in this form. So tau, what this does is it sends the blow-up time lambda times capital T off to tau equals infinity, and rho takes the the rays emanating from the vertex of a backwards light cone with vertex lambda t comma 0. It sends them into vertical lines. So this transforms the backwards light cone into an infinite cylinder. And this has the effect of, in the new unknown, capital U, the original equation transforms into one which I can precisely make sense of the wave maps terms as being small. And so after a bit of massaging, I can rewrite the equation as UTT minus URR minus 6 over R, UR. And so before I write the rest of the terms, let me clarify where this comes from. So when D equals 5, we look over here, when D equals 5, then I, at least for the wave maps term, have a five-dimensional wave equation. And so the wave maps nonlinearities, after factoring out this dependence, this vanishing, I get a seven-dimensional wave equation. But the strong field terms, we have two singular nonlinearities, and so this bumps up the d minus 3 that I get from them to 7. And so altogether, I get a 7-dimensional wave equation minus the transformation of simply the strong field terms, which I'm going to write as F strong field. These are just all the strong field nonlinearities, which depend on U, UT, UR, and also explicitly on R. And then everything else that has an alpha attached to it, which I'm going to rewrite in this way. Lambda squared times some, let's say, alpha plus, I said alpha is 1, so 1 plus, what does it work out to be? 4 sine squared of c over r squared to the minus 1 times, again, the wave maps portion of the nonlinearity minus, which only depends on u, minus the strong field portion of the nonlinearity. So you can rewrite the equation in this way. And it's completely non-obvious whether or not these terms are negligible. But upon making this transformation to similarity coordinates, it becomes clearly visible. You can see, at least there's this small parameter lambda, which is controlling the initial size of that term. So in similarity coordinates, moreover, in a first order formulation, if I were to define a new variable phi of tau to be, so I should also say, I'm going to look for a solution which looks like this, which is 1 over r, u of r over lambda capital T minus t, plus something, and track the evolution of v. And then, if I transform to a first order system, whose components I will call var phi 1 and var phi 2, then I get a first order ODE in these new coordinates. And abstractly, at least, this first order ODE looks like the following. There's some linear portion, which I'll call L naught plus L prime. Momentarily, I'll tell you what they are, times the perturbation phi in these new coordinates, plus the strong field nonlinearity, which is precisely this portion of the equation, plus now in similarity coordinates, there's this lambda squared which pops out. There's, in fact, precisely due to the lack of scale invariance in the precise relationship between the scaling of these two terms, you get an e to the negative 2 tau popping out, times something which I'll call g lambda, which is precisely this term transformed into these coordinates. Now, the precise form of these terms is important. So I'll say the nonlinearities are negligible. And in the remaining 6 minutes, I want to tell you about what's special about these things. So L naught, if I were to simply just look at the equation, L prime dropped and the nonlinearities dropped. This is exactly the wave equation in this formulation. However, that's not quite the case because there's a bit of structure that needs to be taken into account, namely that if you linearize around this null form right here, around this self-similar solution, if you don't take this into account, you basically just get nothing. So nothing for free, rather. So this works out to be negative rho d rho minus 1, negative rho d rho minus 4, 1, and then the radial Laplacian here. So this is, I'll say for the people who are familiar with this minus 4 is not what you would expect. However, this corresponds to a bit of damping that doesn't harm your energy estimates. So L prime, now L prime is quite special. Particularly, there's some compact portion of L prime and a relatively compact portion of L prime. And this relatively compact thing is precisely rho d rho phi 1 minus rho squared phi 2. So the point here is that This term in L prime is a compact perturbation of L0. So if I want to quantify to what extent L prime affects the decay of the semigroup that L0 generates, this portion I can make sense of in a nice way. It won't affect that decay too much. However, this relatively compact portion may be harmful. And so harmful in the sense that I don't have enough time to use the wet eraser, so I'm going to have to use this one. So L prime can add infinitely many eigenvalues to the spectrum of L0 due to the fact that it's relatively compact. So namely, what we can say through essentially energy estimates is that the spectrum of L0 is contained somewhere to the left of -1/2. So the spectrum of L0 is somewhere over here. And then adding L prime, what we can do is precisely say that there's an eigenvalue at 1. This is due to the time translation symmetry of the original equation. But however, according to the analytic Fredholm theorem, as soon as we go an epsilon away from -1/2, there's going to be a discrete set of eigenvalues added here with finite algebraic multiplicity. And because it's discrete, this could go forever in both directions. We can in fact exclude eigenvalues on the imaginary axis. And so, if I want to then upgrade decay of the semigroup generated by L0, what do I want to do? Well, I want to cut out a large enough ball and then show that outside of this large enough ball, my resolvent is uniformly bounded, and then I can upgrade this to decay of the perturbed semigroup after I project away this eigenvalue 1. However, clearly this is not the case because I cannot rule out the fact that there are infinitely many eigenvalues which go off to infinity. And so the savior is precisely the precise form of L prime owed to the fact that this is a null form, linearized around a self-similar solution. And the savior is that this combination L naught plus L prime can be viewed differently. It can be viewed as L naught plus something different, L double prime, up to conjugation by some bounded invertible operator on the space H where I'm solving this ODE. And precisely, gamma applied to something is e to the -1/2, any antiderivative of this first order term, rho v2, times the matrix operator 1, 1, 0, rho 1/2, rho squared v2, applied to v1, v2. And so, in particular, L double prime, if I were to apply it to phi, now the true savior is that L double prime applied to phi is now a compact operator. And so, in other words, in the spirit of Don Lee's result, the derivative can be transformed away through this similarity transform gamma, and such that I get a compact perturbation of L naught, who I can exclude the existence of infinitely many eigenvalues. And however, through this equation, I have an equality of spectra. And so I have L naught plus the spectrum of L naught plus L prime is precisely, at least in this strip, contains finitely many eigenvalues, which I can cut out, get the resolvent bounds I need, and upgrade this to decay. And then through standard arguments, combined with some mapping properties of this extra term, G lambda, and the smallness of lambda, and the exponential decay of e to the -2 tau, the standard fixed point arguments can be closed. So I'll stop there. Thank you for your attention.